Hello students, welcome to the class. Today we will see the theory part 2 of the NCERT chapter 3 chemical bonding and molecular structure. So our today's NCERT section to be covered is section 4.2. This is the disclaimer. Now if I talk about today's objective, then we would be specific about different type of bond that we have dealt till now. Okay, so we'll try to go them with detail and all, see the differences between the bonds that you know already. Now most of the differences must be known to you, but some differences are very peculiar and you should be very appropriate while answering those questions. So we will look on to that also. Now if I move to the specific part of the NCERT sections, then in that first we will see that what is ionic or electrovalent bond. Now we have already seen a glimpse of it in the previous class. In today's class, I will be trying to explain the formation of the same through the help of thermodynamics. I would say a part of thermodynamics which will be easier for you to understand because we have already covered the chapter say classification of elements, but we have not seen the thermodynamics part. So I will try to make it easier for you in that case. Now, the term which I'm talking about is the lattice enthalpy. So this is mostly studied in the thermodynamics chapter. At last, I will give you an exercise of NCERT which is 4.14, which is related to the ionic and the electrovalent bond formation. So let us start our today's discussion. So first, I will go through that what is an electrovalent bond. We have seen its definition. The definition goes like this: the bond which is formed by the electrostatic attraction between the positive and negative ions. So you know it very well that whenever your metals and non-metals combine, they they transfer electron, and in that process, the resultant is ions, and those ions are being attracted to each other by electrostatic force of attraction, in which we get the electrovalent bond, or we also call it as the ionic bond. Now, let us see again the formation of sodium chloride. Now, why I am giving it here? Because in the next upcoming slide, we will see a more detailed discussion on the formation of this NaCl, that how it is being prepared and what are the processes that you go on thermodynamically to prepare this NaCl structure. We know that to make the sodium chloride, the sodium needs to lose one electron. So it is going from a 3s1 to a noble gas configuration. Similarly, your chlorine will be getting one electron from that sodium to make the noble gas configuration, which is equivalent to argon. At last, these two oppositely charged species will just combine with each other to form the NaCl structure. We have already seen that what is electrovalence also. So it is basically the charge that you see on an ion. So if I ask you that what is the charge in case of NaCl for Na and Cl, then your answer would be +1 for the sodium and -1 for the chlorine. So this is the electrovalent bond part, which we have already seen in the previous class. So I am just giving you a quick revision of that so that we can build up a base for the upcoming things. So to understand this thing, first I will tell you what is lattice is without going much deeper into its definition and all. So you know it very well that ionic compounds are solid in nature and they are formed by cations and anions. Now, this cations and anions, they are arranged in a 3D pattern. Okay, why I am telling it specifically that it is arranged in a 3D pattern? Because there are many molecules, I would specifically say covalent molecules, which can be linear in nature. Means it can be two-dimensional. But your ionic compound will always be present in a 3D manner. So they are held together by the strong Coulombic interaction because of the oppositely charged species. So cations and anions, they will apply the Coulombic attraction force on each other. Now coming back to the sodium chloride, which is a crystalline compound, it also follows these two rules. Now it is very interesting to notice that what is the 3D pattern that we get in case of NaCl. You can see here a rock salt structure of NaCl. Okay. Now, what is very good about this? That this represents a lattice. Okay, so this is representing your lattice. If you see here, then the blue balls are representing the chlorine minus. Now, there is a very important question for you. Now, this is related to your previous discussion. You know it very well that this chlorine atom is larger in size as compared to the sodium plus. What is the reason behind it? So it's very simple. We are moving from left to right in a periodic table. So that will result in a larger size for the chlorine atom. And I would specifically say it is chloride atom. Right? Okay. Similarly, if you look at the sodium plus, then it is of smaller size. These two constituents are together combining in a pattern and creating this lattice. Now our duty is to understand that how this lattice is being set up, means what are the processes that we go through to make this 3D lattice. You do not need to remember this pattern. It is not at all important according to your current syllabus. A time was there when you need to learn about the solid state. Now it is not in the syllabus, so you shouldn't be worried about its crystal structure. But to give you an idea that what a lattice is, it was important because we will see the term lattice enthalpy and there you will be confused that what is this lattice meant. Okay, so for that reason I have put up this picture of NaCl lattice. Okay, so it is just not a 3D structure. Basically, you can think it of a repeating pattern. So think of your mathematics textbooks or the math notebooks which you used in the junior sections. So you must have seen that your math textbook was made up of small boxes. Okay, so those were 2D boxes. If you want to take 3 to 4 boxes like this, then you will end up making a plane. Okay, so if you want to make a plane, you will take small square boxes, add them and keep it in a certain pattern, and that will result in a complete plane. Similarly, this lattice can be think of a small cube which will join together, coagulate together and form the whole solid. Got it? So you can define lattice in this way, that they are the smallest repeating pattern that will result in your complete solid structure. Got it? Now we are interested in breaking this lattice, making this lattice and studying the thermodynamics. So let us move on to that. So the next important topic is lattice enthalpy. Definition is the most important part of this lattice enthalpy, which says that it is the energy required to completely separate 1 mole of a solid ionic compound into its constituent atoms. Now 2-3 terms are very important here. The first term is 1 mole of solid ionic compound. So what are you taking? You are taking 1 mole of the solid ionic compound. Suppose if I tell you that you have to take 1 mole of the NaCl ionic compound, then what mass of NaCl will you take? What will be your answer? Again, I am repeating the question. Just think about it. I am telling you that what is the mass of 1 mole of solid NaCl? It's very simple. You know, your sodium is having a mass of 23 and your chlorine is having a mass of 35.5. So that will give you 58.5 as the molar mass of the NaCl. So if I am taking this definition for the NaCl, then I will take 58.5 gram of NaCl. Got it? Okay. Now, what is our next part? We are trying to isolate it into gaseous constituent ions. Suppose you are taking 1 mole of NaCl, that means 58.5 grams of NaCl. Then what is the number of constituents Na plus and Cl minus you will get? It would be 1 mole of Na plus and 1 mole of Cl minus. Because in NaCl the coefficient is 1 for Na and 1 for Cl minus. So let us try to understand it with the help of an equation. Now, coming on to the equation, we are taking the example of a arbitrary ionic compound which is called as Mx. Now, this Mx is made up of two kind of species, M plus and X minus. Okay, and when you combine these two, they will form the Mx solid. But what is your definition? The definition is saying us to separate this. So you will take the reverse of this equation, and the amount of energy you will use to reverse the equation will be your lattice enthalpy. So in simpler terms, if I want to take an example, say we are taking it for NaCl. Okay, then the lattice enthalpy of NaCl is 788 kilojoule per mole. And if I try to define it, then it is the amount of energy you will require to break a NaCl, 1 mole of NaCl into 1 mole of Na plus and 1 mole of Cl minus. So what are the species that you will get upon the breaking of this 1 mole of NaCl? You will get 1 mole of gaseous Na plus and 1 mole of Cl minus. Again, I am repeating this whole part for those who have not understood it at one time. From the start, if I take the first point, then it is saying that you are having a lattice enthalpy of 788 kilojoule per mole for NaCl. Now what this energy is? So it is the energy that you will need to break the 1 mole of solid NaCl into its constituents, which will be in the gaseous state. So suppose you are breaking NaCl solid, then you will get Na plus gaseous and Cl minus gaseous. Again remember, since we are breaking 1 mole of NaCl, therefore we will get 1 mole of Na plus gaseous and 1 mole of Cl minus gaseous. Got it? I hope this is clear to you. It's very important to understand the definition, right? Now, we are well aware about the lattice enthalpy. Now, why this lattice enthalpy is important? Why are we discussing it again and again? And why I am so focused on it? Because this is a very important factor to understand that what are the factors that determine your ionic bond formation. Okay, so I hope you got the point of lattice enthalpy, so that I can move on to the factors of factors which are affecting the ionic bond formation, right? So let us move on to that. Now we will need some previous concepts to understand this factors. The first concept is ease of formation of positive and negative ions for the completion of octet. You know it very well that these elements are doing so to make octet completion. Okay, so if I am saying that your formation of positive and negative ions is easier, that means your solid is much easy to build. So let us take an example for that. Suppose you want to build a house. Okay, and of course for making house you need the cement, you need bricks, you need sand. So these are the major constituents which you will need to make your building. Now, the easier is to get these constituents for your building, the easier would be for you to make that building. Similarly, if you want to make a NaCl, it should be easier for you to make your sodium to sodium plus and make your chlorine to chlorine minus. The more easy is to make these two ions, the more easy is to build your lattice of NaCl. I guess this part is clear to you. So let us take the parameters which decide that how easy a positive ion will be formed and how easy a negative ion will be formed. Now you have already studied this parameter. Can you just focus and think about those parameters that tells us about that how easy a positive species can be formed and how easy a negative species can be formed? For your clue, I am telling you that this is related to the physical periodic trends. Okay. So again, I'm giving you time to guess about that what are the parameters that help you to decide that how easy your positive ion will be formed. So there is one parameter for that, and how easier is negative ion to be formed. There is another parameter for that, and you have learnt about that in your previous class. Okay. Now metallic and non-metallic character, yes, that would be a good information, but that is not related to the physical periodic trends. This is related to the chemical periodic trend, metallic and non-metallic character mostly. Okay, so let us disclose the fact behind it. The most important part to make a positive ion is ionization enthalpy. Okay, so less is the energy required to remove the electron, easier it is to form the Na plus, and easier is to form the Na plus means easier is to form the lattice. So what you can say, that lower your ionization potential or the ionization enthalpy, more it is easier to form the Na plus and Cl minus. Got it? Now what is the second thing that we should be worried about? It is electron gain enthalpy. Yes. So for chlorine or the non-metal, it must be easier for the chlorine to gain the atom or to gain the electron, not the atom, to gain the electron. Now when it will be more easier? In the case if it is negative, in that case it is easier, or in the case if it is positive, in that case it is easier. So for which case it would be easier? Electron gain enthalpy should be positive or negative? Any guesses for that? So we know that electron gain enthalpy can be positive and it can be negative. So in which case it will be easier for the atom to gain an electron? Yes, it should be positive, not negative. Why I am saying it so? Because you are not there to provide energy to your chlorine atom. It is releasing energy, means the process is going on itself in a way, right? Means I am saying that if the energy is released, if it is negative, that means your say atom is easily releasing electron. That is the reason it is giving out energy, or it is going to a more stable state. Got it? So think about it in a way. Suppose you are on a plane and you are driving your car, right? Now suddenly you see a slope, means you have to go on a lower energy. In that case, your car will need fuel? No, it will not need fuel. You can just switch off your car and with the help of brakes and all, you can go down the slope without the exploitation of the fuel, because you are going in a easier pattern, right? So similarly, if something is releasing energy by its own, if you are giving the electron, that means it is easier to attain this X minus. So more negative is the value, more easy for the atom to go into that negative state, because if it is giving out energy, means it is going to a stable state. Is this point clear to you? That why I am saying that electron gain enthalpy should be more negative for the atom to go into the negative part? Okay. Now similarly, the ionization potential should be less and less positive. Now if these two criteria are being fulfilled, means these are the two criteria. The first is ionization enthalpy and second is electron gain enthalpy. If these two are taking place easily, or I would say if the ionization potential is low and the energy that is released is high, that means your negative and positive ions will be formed easily. And if they are formed easily, means they can make the lattice easily. If you have a doubt, you can ask it here. Okay. Now, these are the two factors that we know. And what is the third factor which is important here? It is the formation of the crystalline compound. And that is wholly decided by the lattice enthalpy. Okay. So lattice enthalpy is the third important factor. So again, I am repeating it. First is the ionization enthalpy. Okay. That how easily your atom is losing electron. Second is how easily it is gaining electron. And third is how these two oppositely charged species are coming together and forming the bond easily. Got it? And since they are forming the bond and becoming neutral from a charged species, therefore it will go to a lower energy state and hence it will release energy. So remember always, whenever you combine two opposite charges, they will combine and release energy. So this is the overall picture. Now, what we can say from our discussion through these 3 points, that 3 important points are there that are required for the lattice formation. First is ionization enthalpy, that is removal of electron. Second is the gain of electron, which is decided by the electron gain enthalpy. And third is the release of energy, that how much energy is released when you combine these two. Now lattice enthalpy is the opposite of that. Remember, we have talked that it is the amount of energy that is being used up to break 1 mole of ionic compound into its constituent gaseous state. So if you take this process, then this is the process which is opposite to lattice enthalpy. But we are worried about the magnitude here mainly. Got it? Now, moving on further. We will try to understand that how these 3 things are important with the help of a illustration. So we'll again take the case of our genuine and simple NaCl. Okay, so if I talk about the ease of formation for the positive and negative ions in case of NaCl, then for the Na+, the ionization enthalpy is plus 495.8 kilojoule per mole. So this is the amount of energy that your Na will require to make it to Na+. What about the chlorine atom? So the chlorine atom will gain 1 electron and it will release minus 348.7 kilojoule per mole. Now according to these two factors, if you calculate the overall energy change in the formation of Na plus and Cl minus, then this energy change is plus 147.1 kilojoule per mole. That means in doing this whole process of making Na to Na plus and Cl to Cl minus, you will have to give energy. But we want to make the process easier. What do? Now we look at the third factor. What is that third factor on deciding the formation of NaCl? We have already discussed about it. The third factor is lattice energy. Yes. So the enthalpy of lattice is minus 788 kilojoule per mole. So this is enthalpy of lattice formation, not your lattice enthalpy. Now these are two very closely related terms which are technically different and have different magnitudes and have different signs, not magnitudes, have different signs. So enthalpy of lattice formation is the amount of energy which is released when you combine two gaseous ions to form one solid, whereas your lattice energy is the amount of energy that you will give to break your solid into its gaseous species. Remember, we are doing it on 1 mole. Got it? So this amount of energy is released when you combine Na plus and Cl minus. Now if you add these two amounts, so this is the energy absorbed during formation of Na plus and Cl minus, and this is the energy released when you combine Na plus and Cl minus. This total will give you an energy which is what? Which is negative. So you can just add these two, minus 788 and 147.1. Hence you can say that energy released is more than the energy absorbed. Therefore this process is easier to do. Okay? Why? Because whenever you are losing energy, that means you are going to a more stable state. Since the amount of energy released is more as compared to the energy absorbed, therefore this process is easier to do on a whole scale. Right? Okay, so we have discussed a lot about this. Now moving on further, we have seen the theory part. Now we will do some easy questions which is not related to this lattice enthalpy but related to a Lewis structure. So let us move on to that. Before moving on to that, let me give you a difference table between covalent and electrovalent bond. Now this difference table has some very important points, students. So please look at it very carefully. If you talk about the covalent bond, then we know that it is mainly formed by sharing of electrons, whereas the electrovalent bond are formed by the transfer of electrons. We know these two things very clearly. And if I talk about the covalent bond, then it is formed between two non-metals, whereas the electrovalent or ionic bond are formed between a metal and a non-metal. The third point is very important, and I have highlighted the same. You can see here that it is highlighted and bold both. So your ionic bond is non-directional in nature. So this is very important to understand. When you will move to the further part of this chapter, you will find that your covalent bond, which is explained by the Vesper theory and all, has a certain direction. Means if you take the case of H2O, your hydrogen, oxygen and hydrogen will have a certain relative position, and that is fixed. Okay. But in case of the ionic bond, that thing is not obeyed. So remember this important point, that your covalent bond are directional in nature, whereas the electrovalent bond are non-directional in nature. Then talking about the physical state, covalent bond forms compound which are gases, liquids or soft solids, whereas ionic bond form hard and crystalline solids. Okay. Then next, electrical conductivity. We know it very well that your covalent bond are formed from non-metals, and non-metals are a bad conductor of electricity. So they will not conduct electricity until and unless they are in the molten state. Now what is this molten state? When you take the covalent compound in the solution stage, then in that case there are possibilities of conducting electricity. We will talk about it when we will discuss the electrochemistry part. Whereas your metals which are formed from ionic bond, they are very good conductor of electricity both in molten and aqueous state. Lastly, they have a low melting and boiling point in case of covalent compound, whereas electrovalent or ionic compound have a high melting and boiling point. I hope you got the part of this difference table. So the most important point and the takeaway point is nature of bond, first of all, I would say, and the second most important would be the electrical conductivity. Now we will do a question which is totally based upon the Lewis structure and specifically related to the Lewis structure of ionic or electrovalent bond. Here is your question. Use Lewis symbols to show electron transfer between following atoms to form cations and anions. So potassium, sodium, calcium, oxygen, and aluminium and nitrogen. So I would encourage you further to give me the total number of lone pairs possible for these three species. Your time starts now. So I am talking about the non-metals only. I hope you have analyzed this question as much as possible, and I know it is difficult to answer it here, but let us see. Okay, so we'll talk about the lone pair also. I am talking about the lone pair of non-metal, and you need to draw the Lewis structure also. If I talk about the molten state, then you can think of it simply as the aqueous state. So that is the most simplest and closest terminology that I can use. So you can take the NaCl in the liquid form or the aqueous form, and you can also call it as a molten state. So that would be not accurate to say, but still it is correct. Okay. Let us try to understand the Lewis structure of each of this species one by one. So first, we will talk about the potassium and sulfur. We know it very well that these two are metals and non-metals. So potassium is metal and sulfur is non-metal. So therefore, they very easily form the electrovalent bond in which there will be transfer of electron. If I talk about the Lewis symbol of potassium, then it will be K with a dot. The dot is representing the valence electron. In case of sulfur, there will be 6 valence electrons. That will give you a total of 3 pair of electrons. Now we know it very well that potassium will gain its electronic configuration close to the noble gas if it will lose 1 electron and form K+. Whereas the sulfur will gain 2 electrons and form S2- to gain the noble gas configuration. From here, we need to combine these two. But potassium is having a charge of 1+ and sulfur is having a charge of 2-. Therefore, 2 potassium atoms are required for 1 sulfur atom. Hence, we can write the final Lewis symbol of the compound formed by the potassium as sodium as 2K+ plus S2-. Now, the answer to your question, which I have asked you earlier, that what is the number of lone pair for the case of sulfur? Anyone who is interested to answer this can think about this. It's very easy to see that the correct answer for the number of lone pair of sulfur in case of this ionic compound is 4 lone pairs. Okay, so 8 electrons are there. 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 2 will give you 4. Okay, so on sulfur, 4 lone pairs are there. Now, an important point for you to remember here that this concept of lone pair is not applicable to electrovalent or ionic bond, but I have given you to grasp the previous concept. So it will be majorly used in the, or I would say it will be dominantly used in your covalent bonding and not in your what? Electrovalent bonding. So this is your first Lewis structure of potassium and sulfur. Now we will move on to the next one. Meanwhile, I will encourage you to see the lone pairs on oxygen and nitrogen as well. So our next couple is calcium and oxygen. If I talk about the calcium and oxygen, again, they both are of different categories. So calcium is of metals and Oxygen is of non-metals. Lewis symbol of calcium will be Ca with 2 dots, and oxygen will be O with 6 dots representing 6 valence electrons. Now, to gain the noble gas configuration, the calcium will lose 2 electrons to become calcium 2 plus, and oxygen will gain 2 electrons to form the complete octet of O2 minus. So in case of oxygen, if you see here, then 3 electron pairs are here. Okay. But after the formation, if you see, how many calcium and oxygen are required? So 1:1 ratio is required because they both have same charge. So finally you can write the Lewis structure. Both of the dots are removed from the calcium. So you are seeing Ca2 plus, whereas these 2 dots are now on the oxygen atom. So what is the number of lone pairs here? It is 4 for the oxygen. Okay, with a 2 negative charge. And this is your final Lewis structure. I hope you're getting the solution of this question. It's very easy to see. Now moving on to the next couple and the last one, which is aluminium and nitrogen. So again, aluminium is not a very prominent metal, but still as compared to the nitrogen, and if kept with the nitrogen, it will behave as a metal. The Lewis symbol of aluminium will be aluminium symbol with 3 dots. Then for nitrogen, N with 5 dots. Therefore, we can see it from here that aluminium has 3 valence electron and nitrogen has 5 valence electron. So aluminium will lose 3 electrons to become Al3 plus, whereas the nitrogen will gain these 3 electrons to become N3 minus, and in this way they both will have the noble gas configuration. If I talk about their ratio, then for each aluminium atom you will need 1 nitrogen atom. Hence we can write the complete Lewis structure as Al3 plus, then nitrogen with 4 lone pairs of electron. Therefore 3 negative charge. Yes, it will be 4 lone pairs. So this is all about the ionic and electrovalent bond. Now I will switch on the DPP, attempt the DPPs along with me. Okay. So this is the first question. So there is a question from a student. Sir, we calculate lone pair, then we complete its 8 electron. So what I am seeing it here is that, first of all, this lone pair concept is not that much applicable to your ionic or electrovalent bond. I have just given you an exercise so that you can know how to calculate the lone pairs. And I have given it you to calculate after discovering the octet. That's all. Okay, so you don't have to be panicked about it. So if I am trying to calculate the lone pair, then I would certainly go for other Lewis symbol, which is covalent in nature. Like if I take the case of H2O, then what is the number of lone pair? It is of course 2 here and 2 here. The rest of the 2 is used for the bonding. Okay, is it clear? Any doubt? So this is basically for covalent compounds and not meant for the electrovalent ones. Here is your first question. So, which of the following factors primarily determine the formation of ionic compound? So what we have seen, what was the most easiest way to make ionic compound? The easiest way would be that it should have a low ionization enthalpy, because more easier is to remove the electron, more lower is the energy required to remove it. Okay. Next is, it should have a high negative electron gain enthalpy, because in that case it would be forming the negatively charged species easily, because it is releasing a large amount of energy and going on to the stable state. So what we can say, that the correct option will be option number B. Now moving on to the next question. Is it clear to all of you why I have done it so? If you have a doubt, you can ask it here. Okay, so let us move further. The lattice enthalpy of an ionic compound is defined as energy required to. Option is break 1 mole of solid into its constituent ions in the gaseous state. Then second is form 1 mole of solid from its gaseous ions. Third, convert solid into liquid state. And fourth, separate gaseous ion into neutral atoms. So the correct answer will be yes, option number A. Now if I ask you that what is the term used for the second option, that is saying that form 1 mole of solid from its gaseous atom. We have seen it. What was the term used for this second definition? Anyone who knows it? We have already discussed it. Okay, that what is the term which is used for the formation of 1 mole of solid from its, yes, it was enthalpy of lattice enthalpy of formation. Enthalpy of lattice formation. Okay, enthalpy of lattice formation. So this was the term that was used for the second option. But here we are not forming it. Instead, we are breaking it into constituent gaseous state. So moving on to the next question. Which statement about the stability of the ionic compound is correct? So 4 options are there. Stability depends only on achieving octet in gaseous ions. Second is stability is determined by the sum of ionization and electron gain enthalpies. Stability is primarily due to the lattice enthalpy released during lattice formation or the crystal formation. And the fourth is the stability increases with higher ionization enthalpy of cation. So this is absolutely wrong. Lower is the ionization enthalpy, easier is to form that compound. Okay, so that thing is primarily decided by the lattice enthalpy. Okay, so this is third option will be correct. What about the first one? Yes, it depends upon achieving octet, but it is always not true. Now here is a question for you. Can you give me some examples of compounds which have a expanded octet? Now why am I asking it? For your revision part. Okay, so what were those molecules which were able to form the expanded octet? Anyone who can say about it? I'm talking about the expanded octet, not the duplet. Yes, the correct answer will be PF5. Okay, so we have seen those elements. Those were PF5. Then it was H2SO4. Then we have the SF6. So these were the elements that were forming the expanded octet. So did you try to draw the structure of AlCl3? Anyone? And see that how it is having a limited electrons and not your complete octet. Okay, I have told about it that AlCl3 is having a octet incompletion, but still it is forming a stable compound. Can you tell me that what is the number of electrons your aluminium will attain if it will form a covalent compound with chlorine? Or suppose I am not taking these case, I am taking a simple case rather than AlCl3, I am taking BF3. So what is the number of electrons in boron after making the bond? Is it equals to the octet? So let us try to draw the Lewis structure. Meanwhile, you can give the answer of the same. So I am talking about the bonded state. If you remember the bonded state, then how it looks? Suppose I am drawing the BF3. So your boron will have 3 electrons, okay? It will have 3 electrons. So let me draw it. So first your fluorine will complete its octet, okay? And then after that, your boron will take that same from the fluorine. Got it? Now this will be happening to all of these. Which one? This fluorine and this fluorine. 1, 2, 3, 4, 5, 6. Similarly for this fluorine, 1, 2, 3, 4, 5 and 6. And here is the 7th one. Now you can see it. So I am representing this 7th electron of fluorine with a cross. If you count the number of electrons in case of boron, so what is that count equals to? So that will be equals to 6. Just count it, isn't it? Isn't the octet not complete for boron? If it is sharing 1 electron from each of the fluorine? Yes. Therefore, this boron is having a incomplete octet. Now moving on to the next question. In the formation of NaCl, the sum of ionization enthalpy and electron gain enthalpy for NaNCl is 147.1 kilojoule per mole. What compensates for this positive value? We have seen this, okay. So what was compensating for this positive value? It was your negative lattice enthalpy, which is option number B, okay. So yes, the correct answer will be negative lattice enthalpy, which was compensating for the positive amount of ionization enthalpy and electron gain enthalpy summation. Now moving on to the next question. Next question says that which ion is an exception to the general trend of cations in ionic compound being derived from metallic elements. So this one is a good one, okay. So it is playing with your language part. It's very easy to understand the question. Once you understand it, you will get your answer. So the question is saying that out of this, which one is a cation and still it is not derived from a metallic atom. So this is the only cation and it is derived from the metallic atom, but this one is derived from non-metal. Therefore, your correct answer will be option number C. So this is your correct answer. You got my point, right? Okay. So your time is up. Let's see what we have done. Okay, so all our answers are absolutely correct. So if you have a doubt, you can ask it now. Then let me give you a task for the remaining 2 to 3 minutes. So in few minutes, our math faculty will be here. Can you draw the Lewis structure of NO2 minus? If you can do it so, then can you calculate the number of lone pairs on it and the number of formal charge on each of the elements? So I am trying to tell it for the NO2 minus. Okay, so I am trying it slowly while explaining each and every step, so you can try it by yourself. Okay, so you have a doubt in last question. Let me see. So the question is saying that out of these given species, which of the species is a positive one? Because it is written that it should be a cation, but still it is not derived from a metal. Okay, so these are the two species which are positively charged, but the last one is derived from a metal, whereas this NH4 plus is derived from a non-metal. The non-metals are nitrogen and hydrogen. Is it clear? Okay. Now my question remains here. You are taking the species as NO2 minus. So anyone of you, can you try and just draw the Lewis structure and tell me two things. First is formal charge on nitrogen. Okay. What is the formal charge of nitrogen in this case? And second is that what is the number of total lone pairs? Any guesses for this? Anyone? So I will try to draw it slowly so that you can give the answer before me. First, I will draw the nitrogen. Here oxygen, here oxygen. So this was our first thing. Then we assign the lone pairs onto it. Okay, I have assigned it. 1, 2, 3, 4, 5. Till this part, any doubt? Okay. Now, if I ask you that what is the total number of valence electron in case of NO2 minus, then what will be your answer? Total number of valence electron. You have to simply count the number of valence electron in case of NO2 minus. What would be your answer? So 3 species are here. What are those? Those are nitrogen, oxygen, and a negative charge. So the third part is negative. So 7 for nitrogen, 2 8 is 16, 2 6 is 12, sorry, for oxygen, and 1 for the negative charge. So this is 6. Just added. So 12 plus 17 plus 1, 19 electrons. So 19 valence electrons are possible here. Okay, so I've already got an answer. There are 5 lone pairs. Let's see if you are correct or not. So are you clear about this, that there are 19 electrons in total? Valence electrons in total, or NO2 minus? So if you have a different argument, you can ask it. Then why you have taken it 19? Anyone? Okay. So how many electrons are already in this skeletal structure? If you count it, so let me use a different marker for that. What are those electrons? First, second, third, fourth, fifth, sixth. Similarly, 6 here, 6 plus 6, 12, and 12 plus 5 will give you 17. Okay, so here it will be 5. Okay, yeah. So here I have done a mistake. Sorry for that. So 5 will be here because 5 valence electrons are present in case of nitrogen. 7 is the total number. So that will give you a total of how much? 12 plus 5, 17, 118 electrons. Yes. Okay. Now, in this case, sorry for the disturbance. Okay. For this case, if you see that only 17 electrons are being possible if you simply draw the Lewis structure. But actually your overall electron should be 18. So 1 electron is missing here in your Lewis structure. You got my point? Any confusion in this? Anyone? They can ask it. So what I am saying that if you draw the relative structure, Lewis structure, without taking the charge, you will get 1 less electron. So that is obvious. Now you have 1 extra electron to be put here. Where we will put? We have 3 options. Or I would say these 2 are similar option. If you will put here and here, that will not matter. But your option is between nitrogen and oxygen. So what would be your choice on putting this extra electron? Where it should go? Any guesses? Out of nitrogen and oxygen, where should this extra electron go? You can relate directly it with the electronegativity. Remember, the element which will get 1 extra electron, that will have a negative charge on it. Yes, the correct answer will be oxygen. So your extra electron will go where? It will go on to the oxygen. Now your question arises, why it is happening? Why it is going to the oxygen? Why it is not going to nitrogen? Because your oxygen is a more electronegative element as compared to the nitrogen. Therefore, you will put the extra electron on the oxygen atom. Is it clear? No issues if you have told it wrong. If you got the idea of putting this electron on oxygen, then it is good enough. You got it? That why I am putting it on oxygen? Because oxygen is more electronegative. So it will be a much easier bearer of this negative charge, because upon giving 1 extra electron, it will be having a negative charge. So I'm giving the negative charge here. Now coming on back to the question that how you will complete the octet now. So let us try to do this part now. So I'm going step by step as slow as possible. Just follow me and you will get your answer very easily. So your oxygen is already having 7 electrons. So how many electrons it will require? It will require just one single electron. So I will make it. So this will take one electron from oxygen. Similarly, your nitrogen will also take one electron from oxygen. Any doubt? What about this oxygen? Since this oxygen is only having 6 electrons, so it will take 2 electrons from the nitrogen, and same will be done by this nitrogen onto this oxygen. So you can extend your boundary and take this 2 electrons from the oxygen. So if I draw it clearly in one go, then it should look like this. N, okay, then oxygen with a negative charge, then oxygen here. So this is the complete structure of your NO2 minus. So there are 2 electrons left on the nitrogen, I guess. So the first one is here and the second one is here. And yes, there is a possibility for 1 electron also. How? Now only 1 electron is left on the nitrogen. Can it be considered as a pair of counting the lone pair? No, it cannot be considered if it was single, but here it is not single. Right? It is not at all single here. 2 are present here. Okay. Now coming back to the question, I was asking that what is the formal charge on nitrogen? If you calculate the formal charge, so I am giving this task for your homework. You will try it by yourself. Just after the class, it will be 0. Okay. So the formal charge on the nitrogen will be 0. You can calculate it. And what will the number of lone pair? It's very easy. So 1 lone pair, 2 lone pair, 3 and 4. We will not count this because it is not a pair. So 4 lone pairs are possible. Got it? Okay, so this was all for today's class. Thank you for attending the session.